endomorphism rings and Tate modules. So first we start with endomorphism ring. So let A and B be Abelian varieties over K. And F, G be homomorphism. Then we can add these, we can define the addition of F and G. Can add F and G as follows. So we want to say that F plus G of X is equal to F of X plus G of X for all X in AK bar. So doing this, so this gives the set AB, the structure of an abelian group. Okay. And in the case when A is equal to B, this is even a ring. So when A is equal to B, we let and A home of A into A. And in this case, this is a ring. And where the multiplication is given, just composition of homomorphism. Okay. So, and of course, here we have to be a bit careful because sometimes we want to talk about endomorphism that are defined over the base field or not. So, what we are going to do in that case, so we will use the notations on KAB and KA for the homomorphism that are defined over K. So homomorphism or endomorphism defined over K. Okay, so that will avoid any kind of confusion when we are talking about this object. So the first lemma that we are going to see is basically telling us this homomorphism group is a torsion-free group. So it's the following lemma. It's the first lemma we are going to prove today. So we let A be abelian variety over K. Then the group home AB is torsion free. So meaning that for if we take F in home AB and an integer n which is non-zero, then n times f equals 0 imply that f is equal to 0. Okay. This is a fairly easy lemma to prove, so let give it the proof. So take an integer and let f be a homomorphism of A into B, right? Then it's easy to see that we have the following. So then we can see that if I take n time, sorry, we see that if I take n time f, this is simply taking the composition of, so this is simply, by definition, this would be taking the multiplication by n on B composed with f, but we'll see that this is the same as composing f with the multiplication by n on A. And the key observation here is that, let me rewrite this better. But we know that it's an isogeny. So it's surjective. And so from this, you see that we see that if n times f is equal to 0, this would imply that f is equal to 0. Okay. So that's the first result that we're going to see. And now I'm going to give some definition that we are going to use in most of, for the rest of our lectures. So we write, so we are going to write home 0 of AB. Whenever I write this, I mean that I'm taking home AB tensored with Q. And then whenever I write end 0 of A, I mean that I'm taking the endomorphism ring of A, and then I'm tensoring with Q. And of course, by definition, we see that if this endomorphism ring is a Q algebra. In fact, we are going to give a very precise description of this endomorphism ring a bit later. But for now, we are going to discuss of additional properties of abelian varieties. Okay, and the first result that we're going to need in that direction is the following, which is a theorem called the Poincaré. It's called the Poincaré reducibility. Okay, so in this case, we let A be an abelian variety. So this is an abelian variety, and we let B be a subvariety. So B is an abelian subvariety. A. Then the theorem says the following. So the theorem said there exists an abelian subvariety So you have an abelian subvariety C of A. Is there exists an isogeny from B cross A, B cross C to A. Okay. The proof is this theorem is actually not that hard, but I'm not going to give it here. But in any case, you do have, I gave some the main ideas of the proof in the lecture notes. Okay, so granted the theorem, we have the following definition. So let A be a non-zero abelian variety over K. This is, then we say that A is simple we say that A is simple if the only non-zero subabelian varieties of A are 0 and A itself. Okay. So that's the definition of a simple subabelian variety. And if you look at this definition carefully, you would see that you have to be careful when it comes to the ground field. So that's the first observation, which is that if you start, A can be simple over K, but not simple over an extension K prime of K. Right, so the field over which your abelian variety is simple is very important. So with this in mind, we are going to say that we are going to use the term K simple to mean that the abelian variety is simple over K. So we will write K simple to mean that A is simple over the base field K. Okay. And now here comes a very important proposition, which says that every abelian variety would decompose into a product of simple abelian varieties up to isogeny. Okay. So let A be a non-zero abelian variety over K. Then the proposition says that then A is isogenous to a product of K simple abelian varieties. So what does this mean? So more precisely, there exists K simple abelian varieties, which I'm going to call K simple abelian varieties B1, B2 up to BR. And these one are pairwise non-isogenous. So they are pairwise non-isogenous. And non-negative integer, and sorry, positive integer N1, N2 up to NR, such that A is isogenous. This is the notation we are going to use to mean isogenous to the product of B1 up to BR to the NR. So that's the first part of the proposition, and the second part says that up to permutation, this decomposition is unique. Up to permutation is unique. Okay. Meaning that if you permute the factors, any decomposition would just consist of a permutation of these factors with the same exponent or multiplicities. And the proof is really just, I'm going to leave this as an exercise because it's really just applying the Poincaré. This is an immediate consequence of the Poincaré reducibility proposition we just saw. So the Poincaré reducibility theorem. Okay. So now, as a corollary of this, we are going to give a description of the endomorphism ring of an abelian variety, which is a bit more refined than the description we saw as just being a Q algebra. So that's the next corollary. So the corollary says the following. So we start with an abelian variety over K. And the first item says that if this abelian is simple, if A is K simple, then if you look at the endomorphism ring over K, then this is a division algebra. Okay, that's the first part. And the second part of the statement says that if, on the other hand, A is isogenous over K to a product of simple abelian varieties, so where the BI are K simple, then if you look at the endomorphism ring of your abelian variety A, in that case, you would get that it's basically a product of matrix algebras over division or division algebra. So this would be N1 D1 cross MNR DR, where DI is the endomorphism ring of BI. And the first part of the lemma tells us that this endomorphism ring is a division algebra. So you get that the endomorphism ring of your abelian variety A is just a product of matrix algebra over division algebras. Okay. So that's what we are going to say about the endomorphism ring of abelian varieties for now. So in the next part, we're going to talk about Tate modules, and then we will discuss the relation between these two sets of objects a bit later. So now the second part is the Tate module of an abelian variety. Okay. So again, the setup is that we start with an abelian variety A over K, an abelian variety, and throughout we're going to we're going to assume that the dimension of our abelian variety in this case is G. And then we are going to let n be an integer we are going to let n be an integer or such that n is prime with the characteristic of the base field. So that would be the main assumption. And then from this, I want you to recall that we saw that in the first lecture, we saw that under those assumptions, if you consider the multiplication by n map, which goes from A to A, then this is an isogeny. Not only it's an isogeny, but it's one that is separable. Oops. So this isogeny is separable and has degree of degree n to the 2g. Okay, so we saw this. And of course, what that means is it means that the inverse image of any point by this map would have cardinality n to the 2g, right? Hence, each fiber of this map has cardinality n to the 2g. Okay. Now let an be the kernel of our map. So we used this notation last time. And the corollary, one of our corollaries that we saw last time. So not only an has cardinality n to the 2g, but we also saw that an as an abelian group, it would be isomorphic to z mod n to the 2g, and this isomorphism would be as abelian group. Or you could even say as n over mod z n modules. Okay. And so this is something we are going to use. So using this, we can now define what the Tate module of this abelian variety is. So the Tate module of, so now if I take, so let L be a prime, such that L is not equal to the characteristic of K. Then we define the L dictate module, so the L dictate module of A is which we are going to denote by TL of A is defined as follows. So it defined as we let TLA be the inverse limit the inverse limit given by the torsion subgroup. Here the transition map. The transition map are simply the multiplication by L. Right. So that's what of TL. We see that in fact we would have an isomorphism of this to the 2G. So, okay. One important aspect of Tate module is that it comes equipped with a Galois action, and that's something which is really, really, really useful. So, extremely important. So, an extremely important property of Tate modules is that they carry a Galois action. Right? So, so if K is not algebraically closed, so if you start with a field which is not algebraically closed, then we see that the Galois group of K bar, where K must this must move the torsion point around the and so as a result you get that this group this group would have an action, it will come equipped with an action of gal K bar over K. So if K is not algebraically closed, then gal K bar over K must move the torsion point around. And this, of course, would carry through. This would be compatible with taking inverse limit. And so, so as a result, we get that gal K bar over K acts on TL of A. And if you pick a basis, so picking a basis of TL we can write that action as a representation which is gal k bar over k to GL2G ZL. Okay, so this is give this L-adic representation. Okay. And there is some kind of functoriality that comes with this, namely, if you give yourself a homomorphism, so let F be a homomorphism of abelian variety, so if you have a homomorphism of abelian varieties over K, then we see that F will induce it in fact induces a ZL linear map a ZL linear map we are going to denote by TL of F from the Tate module of A to the Tate module of B. And not only that this map is ZL linear, is so this map is in fact Galois equivariant, so it would be a Gal K bar over K equivariant map. Right, and of course this map it's kind of defined in a very natural way, right? So if you have X as X0, 0, X1, X2, and so on. So TL of F applied to X would simply be applying, if you apply F component wise to this sequence, you'd get a sequence which is compatible with taking inverse limit, and that's how you get you get this map. Okay. So an important theorem that we are going to need is the following, which is that it's the following. So let A be abelian variety and L a prime, which is different from the characteristic of the base field. Then the Z linear map, then the following Z linear map is injective. So the Z linear map, or TL, so this map is going from of A, B, and so with ZL to the homomorphism over ZL of TL of A, TL of B. And this map, you take F tensor C, and then you send it to C times TL of F. And the theorem says that this map is injective and with a torsion-free cokernel. Okay. I'm not going to give the proof of the theorem here, but I'm going to give some indication for those of you who want to read about it. But yeah, but this would going to be a very important theorem for us a bit later. It's a key element. So basically, in some cases, the Tate theorem says that this map is in fact an isomorphism. So that's what we're going to see later. But before we do this, we are going to see additional properties of Tate modules. So the next thing that I'm going to discuss is this would be a relatively short. So the Tate module of the multiplicative group. So in fact, if you look at what we've done so far, you can define the Tate module for basically any group scheme in essence. So we can define Tate module for most group schemes. So what we're going to do now, in this case, we are going to consider, the multiplicative group. So consider the multiplicative group. GM, right? So you can view this GM as spec of K, where we take T and T inverse, right? And so what are the torsion subgroup of GM? So take if you give yourself an integer, if I give myself n in Z such that n doesn't divide, n is coprime with the characteristic of my base field, then of course we see that if I'm the n torsion point of this group scheme would simply be the n root of unity, right? So okay. And so we can basically mimic what we just did for the n torsion of an Abelian group. Right? So of course we see that as an Abelian group, so right? So as an abelian group, we know that if we take the k-bar point of this which we said is mu n. So as an abelian group, this is isomorphic to Z mod nz, right? So we can, so by using the same kind of construction we did earlier, by the same approach as earlier, we see that if we look at the third module of Gn, it would simply be right. So it's the inverse limit, and here we have mu to the Lm m, and this is going to be isomorphic to ZL. And as before, this also has so as before, has a Galois action. Right? And this action is given by what we call the cyclotomic character. This action is described by a character. This action is given by a character right? So we basically, what we have in this case is that because this is the TL is just a rank 1 module over ZL, the action would be given by 1-by-1 matrices, and of course this is isomorphic to ZL cross. And this character is known as the cyclotomic character. Okay. Sometime we are going to use a notation. Sometime we will use the notation in fact it's quite common, the notation ZL1 for TL of GM. So basically what this notation means is that it's simply saying that the Galois group act through the first power of the cyclotomic character. So to mean that gal k bar over k acts first power of cyclotomic character. So that's what the notation will mean in this case. Okay. So now we're going to talk about the notion of veil pairing, and which is something we are going to need a bit later. Okay. So for veil pairing. Okay. So we're going to start the discussion about veil pairing with a proposition about the existence of such pairing. So the running assumption is that V A over K is an abelian variety, and N is an integer which is co-prime with the characteristic of the field. So okay. Then the proposition says that there is because what I'm saying here is not quite correct. So the second property is what I'm going to call the degeneracy, non-degeneracy. Okay. So non-degeneracy. So this means that if I take if En of x, y is equal 1 for all x, if this is equal 1 for all y in a dual n, then this would imply that x is equal to 0. And the third property is that the map is Galois equivariant. So if we take En of sigma x, sigma y, then this would be the same as taking sigma applied to En of x, y. And of course, for all sigma in our Galois group, okay. And the other compatibility condition that I want to state is the following. Compatibility. So if you take x in AMN and you take y in AN, A dual n, then you can compute EMN of x, y by taking En of mx, comma y. So that's the compatibility condition. So yeah, so those are the main properties of this pairing. Now, the one minor remark that I'm going to say before going further is the following. It's that we are using tell you now what we get from this pairing when we start with an abelian variety which is equipped with a polarization. So assume that A is polarized, so meaning that we have a pairing lambda. Then you see the pairing. So the pairing En induces a pairing which I'm going to call En lambda. And in this case, this pairing goes from An cross An into mu n. And in this case, you send x comma y to En, apply to x comma lambda y. And we call this a veil pairing. En is also called a veil pairing, by the way. And this pairing, it does make sense to talk about being an alternating pairing, because now I'm pairing An with An itself. So so in this case, you get a pairing which is what we call alternating. So in addition to the properties above, above proposition, the En lambda is alternating which in this case mean that if En lambda of xy is equal to En lambda of yx inverse. Okay. So now here some other properties of this pairing. So the pairing satisfies this pairing satisfies the following compatibility property. And what is that compatibility property? Is the following. Okay. So you have polarized abelian varieties where so lambda A is the polarization on A, and lambda B is the polarization on B. Is compatible with the isogeny and its dual in the following sense. So if you take En lambda A of f of x, comma y, then you get that this is En lambda B x, comma the dual of f applied to y. And this is for properties that I'm going to state in this lecture is the following. So, of course, so if you notice the construction we did, so the construction of the pairing is this pairing is compatible. So the pairing ELN lambda are compatible with inverse limit. So as a result, we are going to get so we will have a pairing on the third module, which we simply call E lambda, which goes from TL of A cross TL of A into ZL. Above. So the same properties of bilinearity and skew symmetry as above. And of course it's compatible so it's also compatible with the Galois action. Okay. Okay, so this is what I want to say in this lecture. So we are going to return to some of these properties in the coming lectures. Okay, thank you.